Good day, ladies and gentlemen. This is our second video talking about the ideal gases and their thermal properties. The first video we spoke about ideal gases and real gases and differences between them, and we spoke about Boyle's law. And I would highly recommend that for this work you make a little cheat sheet almost, where you have the law followed by its equation, which in Boyle's law would be P1 V1 equal P2 V2, and then followed by little example, maybe just something to help you to keep the formula and the law and its description very neat and orderly. Now, continuing on with our next one, we now had Boyle's law, we now have Charles's law. And Charles's law is about the temperature and the volume. Mr. Charles, I believe, was a French scientist, Jacques Charles, and he had a gentleman help him, Joseph Guy Lussac, I believe. Not a particular history buff. And what they pretty much did was they plotted the volume of a gas against the temperature. So what is the volume of a gas at 10 degrees? What is the volume at 15? What is the volume at 20? And they did this experiment and they came to their law. Now, same as we had with Boyle's law, we can draw a little graph for this. And what pretty much happened was they found that if you have the volume increasing like this, and you have temperature over here, 0, and let's just say 500, and over here negative 300. What they found was that as you increase the temperature, the volume increased. So we had something going a little bit like this for our different gases. As the volume of the gas increased, well, it was a result of the temperature. And what they found was that if you then plot these graphs backwards and you get to a theoretical point, this point over here, negative 273.15 degrees Celsius, what they sort of found was that, theoretically at least, by plotting the graph that they found backwards, at that temperature the volume would be equal to 0 because it's so cold. Now, this is significant for a few different reasons. First of all of the gases that they did this for, and they plotted lovely little graphs, and when they worked them backwards, all of them intercepted at this temperature. Now, of course, they couldn't actually cool anything down to that temperature, so it was only theoretical, but they all got to that temperature. And later, a gentleman named Kelvin, British I believe, realized the significance of this, and he called this temperature absolute zero. And you might have heard of something called absolute zero. Absolute zero is equal to negative 273.15 degrees Celsius. And absolute zero is theoretically the lowest possible temperature achievable by anything. At this temperature, absolute zero, theoretically there is not even enough kinetic energy in the particles that they can move. Nothing can happen at that temperature. Now, this gentleman, Lord Kelvin, also set up a temperature scale at which absolute zero was the starting point. On the Kelvin scale, 1 Kelvin is equal to 1 degree Celsius. The only difference between the two scales is that the 0 point starts shifted. So you could say that absolute zero is 0 Kelvin and negative 273 degrees Celsius. The freezing point of water is 0 degrees Celsius. That is 273 Kelvin. The boiling point of water is 100 degrees Celsius, and that is then 373 Kelvin. So the only thing that really changed was that he made absolute zero 0 Kelvin, and everything from there you count upwards. So when you get to 0 degrees, you are at 273 Kelvin. Now, this is a little bit of a side note, actually a lot of a side note, but it is still actually important. You might have heard something about kelvins and degrees Celsius, and the easiest way is to say, to convert from degrees Celsius to Kelvin, you say plus 273. To convert from Kelvin to degrees Celsius, you say minus 273. Now, T is the abbreviation for temperature in Kelvin, and a small letter t is temperature in degrees Celsius. So we can say that from Celsius to Kelvin would be T is equal to small t plus 273. Kelvin to degrees Celsius would be small t is equal to t minus 273. Now this is actually a very large tangent on Charles's law, but it is still important, specifically this bit and the actual theory of absolute zero. And I do apologize if I've gone on too much of a tangent, but the idea of absolute zero is still important. This is, however, the limit of what we will be discussing in absolute zero for this point right now. If you want a more specific video with all the details in absolute zero, let me know, we can make a plan. But moving forward, Charles's law, almost forgotten about them, stated that the volume of a fixed amount of gas, because again we try to keep things simple, so we say a fixed amount of gas. I can't spell anymore. Maintained a constant, I really can't spell anymore, a constant pressure that is directly proportional to the temperature of the gas. So what this just says is that the volume of the gas is proportional to the temperature of the gas. That's all. Now, this formula we can move around a little bit. Now, we can also then say that same thing as we did with Boyle's law, is we can say that we move this around a little bit and we say that the volume is constant and everything, and that gives us V is equal to constant at temperature. We can also rewrite that by taking that K out. V over T is equal to the K. And this means that we have exactly the same thing we had with Boyle's law. If we have a fixed amount and we have a constant pressure, the only things that are changing is the volume, the temperature. So just like in Boyle's law, we had a constant temperature, we only had volume and pressure changing. We can now say that in one instance, we are going to have the volume and the temperature, and they will then be equal to the volume and the temperature of that same gas at a different instance, provided the amount stays the same and the pressure stays the same. And this, in essence, is all you need to know about Charles' law. Now, let me follow my own advice. We have Boyle. Oh, I really cannot spell today. I do not know what's going on with me. How do you even spell Boyle's law? I completely forgot. Boyle's law. And Boyle's law was P1 V1 equal P2 V2. We then had Charles, and that is V1 over T1 is equal to V2 over T2. And of course, P is equal to pressure, V is equal to volume, and T is temperature. So let's put this aside and we'll add the other gas laws to them as we continue. Now, the next one that we have to look at is Mr. Charles's associate, Mr. Guy Lissac. Guy Lissac was more interested in the pressure and temperature. And what he did was he had a fixed amount of gas with a constant volume. That is to say, a certain amount of gas was inside a container, so the amount stayed the same, and that container, being a sealed system, the volume stayed the same. And then he fiddled with the temperature, which caused all kinds of funky things to happen with the pressure. Now, Mr. Guy Lissac's law states that the pressure of, again, a fixed amount of gas is directly proportional to the absolute temperature. And this absolute temperature means in Kelvin. And that is why we had that little K when we were talking about Charles's law as well. Now this means pressure proportional to temperature. We can again write this. Pressure is equal to Kelvin temperature. And we can then move that around exactly the same as we just did with Charles's law. And we end up with exactly the same thing we had previously. If we have a system where the pressure is what we are investigating, we have a constant amount, a constant volume, the only thing that can change are pressure and temperature, we end up with a gas where the pressure and temperature in instance 1 will be equal to the pressure and temperature in instance 2. We then, of course, can add that to our list. Guy Lissac, P1 over T1 equal P2 over T2. Now, you can see we've got a few little formulas here. And that's pretty much it right now. However, of course, things get more complicated. And things get more complicated thanks to a gentleman called Avogadro, or Avogadro. He was an Italian scientist, I believe. And he sort of looked at these things that Mr. Boyle, Charles, and Guy Lissac did, and he decided that those don't quite cut it. So what he did, and if you were to then, as we've been doing, state Avogadro's law in a sentence, he said that at a constant pressure and temperature, so the pressure and the temperature are constant, the volume of the gas is directly proportional to the number of molecules in that gas. That is to say, the amount of gas molecules. Now, intuitively, this should make sense, because if we have a container, and that container has a constant pressure, a constant temperature, nothing is going to be changing in that. What is going to influence the volume of this container that is quote-unquote filled with gas is going to be the amount of gas molecules that we have. And what he then said was that the volume is proportional to the number of molecules. And this is where things get a little bit interesting, shall we say. Because we can now take everything we've done up to this point, and we can say that for Boyle's law, we said volume is inversely proportional to the pressure. If we have a constant amount of gas, N is the number of gas molecules, and temperature. For Mr. Charles's law, we had volume being volume proportional to temperature at a constant amount and pressure. Mr. Guy Lissac told us that pressure is proportional to temperature, again at a constant amount and volume. And then Mr. Avogadro told us that the volume is proportional to the amount of the gas at a constant pressure and temperature. So if we then take all of this together and we want to summarize everything, then we will say that for a fixed amount of gas, that is to say N is constant, we have what we call the general gas equation. That is the pressure, volume, and temperature of one is going to be equal to the pressure, volume, and temperature of 2. And we call this the ideal gas equation because this does sort of explain everything we've been looking at. Because what we have is we have N being constant, we have pressure, volume, and temperature, which are the things we've been looking at. Now, we can, of course, sort of rewrite this, and we can say that, well, we've got our general equation, which has everything we've been looking at so far. We then have the ideal gas equations. These are a bit more specific, shall I say. We have V, volume, proportional to the amount and temperature over the pressure. Or you can say that the volume is equal to RNT over P, and we can then change that once more to say pressure times volume is equal to the amount of gas, or times temperature. R in this case is a constant, the universal gas constant, and that is equal to 8.31. So what we in essence have, is we have the pressure and the volume being equal to the amount of gas and the temperature of the gas, with a constant we use to make things work a little bit better. Now, this is pretty much it. We have our general equation and we have our ideal equation. Because remember, ideal gases behave differently than the general gases. Ideal gases sort of are these perfect gases that just work amazingly and easy. And then we have the actual real gases where things get a little bit difficult. So we can then take our formula and we can say we have an ideal gas law and we have a general gas law. The general gas law being P1 V1 over T1, P2 V2 over T2. I apologize, I've confused them. This is the general one, and this is the ideal one. I apologize, ladies and gentlemen, a slip of the hand. Pressure V equals nRT, where R is a constant. And if you would like some examples worked out on this, you need to let me know so we can make a plan. But in general, any textbook that's actually worth its salt should have some examples on these gas equations and stuff like that in them. So you can just work through examples in your textbook. Now, moving on from there, the only thing really remaining for this whole pressure, temperature, gas thing is the idea of temperature and heating. And I briefly discussed that in our first video where I said that the pressure is related to the particles colliding with the sides, and that the higher you heat up the gas, the more pressure you will have because the higher temperature causes more collisions. Most textbooks make a point of explaining temperature and heating as a function of pressure. And in general, that's just a tiny bit of theory that you can just familiarize yourself with. It should not be too much. That is it for the ideal gases and the gas laws. If you'd like some worked out examples, like I said, your textbook should have them, but if you struggle, let me know. If you are actually one of the students in my personal science class, I have the same textbook as you, so I can give you the page numbers or something like that if you'd like. That's it, ladies and gentlemen. Until next time, have a nice day.